So our second speaker today is Tobias Kaiser from Passau, who will speak about his work with Andre Opris, who is also on, differentiability properties of log-analytic functions.
Thank you very much for giving me the possibility to talk about our research. So it was my PhD student, Andre, also in the audience. And it relies on the work of another person in the audience, namely Jean-Philippe. Hello, Jean-Philippe, nice to have you here. So I start with the motivation. So nowadays, humanity is very successful regarding applications, most notably in number theory, arithmetic geometry, and the most relevant open structures regarding applications are the structure AAN, so the structure generated by the restricted analytic functions. So what is a restricted analytic function? It's an analytic function restricted to a compact hypercube. And the definable sets, respectively functions, are precisely the so-called globally subanalytic ones. And then we expand this structure by the global exponential function and obtain the structure of restricted analytic functions and the exponential function. And as we already have heard, there is a dividing line from the analytic point of view. Why? So on the left we have RAN, on the right we have RANX. Well, RAN is a polynomial bounded structure, RANX is not polynomial bounded. RAN we have phenomena of analyticity, so functions are analytic, and if there's infinity, they are already analytic. In the second subnomial structure, we have no quasi-analyticity. In the first structure, so-called Thom's theorem holds. In the second one, it does not hold. I will explain it later. So 1 and 2, we are of course familiar with that. The exponential function is of course not polynomial bounded. Second case, second instance, this is the standard example we know from calculus. This function is definable in Rx. It's a C infinity function, but it is not analytic. So it's a flat function. So in the origin, the Taylor series vanishes, but the function is not the zero function. So we do not have quasi-analyticity. In the first structure, we have really strong analyticity. That's Thom's theorem. So named after the mathematician Thom, who has published a version of this in the Acta Mathematica. Here I present the version of Van den Bries and Miller, which have extended this result a little bit. So let f from Rn times Rm to R, so x is in Rn, y is in Rn, be a globally subanalytic function. Now I think of x being the parameter, y being the variable. Then there is a natural number big N such that the following holds for every xy. If fx is Cn at the point y, so x is here fixed, and if this is a Cn function at the point y, then this function, depending on y, is already real analytic at y. This means from a certain point on, there is no gap between Cn and real analytic. Of course, this big N depends on the globally subanalytic function, depends on the function definable in Ran. If we have the exponential function, Thom's theorem does not hold at all, even if we replace real analyticity by C infinity. That's the following example. We consider the following function depending on two variables. X, y is mapped to the absolute value of y to the absolute value of 2x if y is not 0, and if y is 0, I put it 0. Then this is definable in this structure. Then the set of all x in R such that the function fx variable, the second component, is real analytic, or C infinity is the set of integers. So it's not definable in any OMR structure. Here we leave the Tain setting. So if we have the exponential function, then Thom's theorem or some version of Thom's theorem does not make much sense in the Tain setting. And this dividing line from the RAN structure to the RANX structure comes really from the exponential function. Well, the smallest obvious. Exponential function gives flatness, gives C infinity, but not analyticity. So what is our goal? Our goal is to go beyond this structure, to go really into this structure, but still to have nice analysis. So the goal is to identify a natural family of functions. The family should go from the point of view of definability beyond this structure. So it should even generate a bigger structure, but not from the point of analysis. And what is the idea? Do not work with the exponential function, work with the logarithm. So idea, log-analytic functions. Well, this idea is not new. Log-analytic functions has been well introduced, considered by Jean-Philippe Rollard and Lyon in their seminal work, middle of the 90s. And we build on their work to get results for analysis. Now I introduce log-analytic functions. Here the setting, by definable, we mean definable in the bigger structure, including exponential function, definable with parameters. And we always use the word piecewise. Piecewise means that there is a decomposition of the ambient space, so some Euclidean space R to the n, into finitely many definable sets, such that the given property holds on each piece. And here is the definition of log-analytic functions by Lyon and Rollard. So a log-analytic function is piecewise an iterated composition from either side of globally subanalytic functions and the global logarithm. and we say that a function is log-analytic of order R if it is log-analytic, and I need there the logarithm R times to construct it. If the logarithm is there in R times nested. Let's consider an example, this function here. So there we have something algebraic, then we apply the logarithm, we add something algebraic, apply the logarithm, something algebraic, logarithm, here applying the arctangent, which is globally subanalytic. So this is a log-analytic function where we have of order 3, we have 3 times the logarithm. Yes?
So this is of order at most 3, right? Because, or is it obvious that you can't write it?
No, you're right, it's of order at most 3. But one can show by growth axioms that this is of order 3.
I didn't hear you, I'm sorry, I had a connection problem. So you say it is 3, but it's not important, right? It's okay to
Not important and it's not obvious.
Okay.
Yes, but you're right. From the model theoretic point of view, the log-analytic functions can be described in the following way. So L is the language of ordered rings. We augment it by symbols for every restricted analytic function. We get the language LAN. That's the natural language for RAN. We know by big result of Van den Dries and McIntyre and Marker that the functions definable in here, so the globally subanalytic functions, are piecewise given by terms in LAN, a symbol for the inverse functions and for the nth roots. Then I also augment this language by the logarithm, and the log-analytic functions are precisely those terms. So really everything, but not the exponential function. Okay, so from the point of definability, so to write log-analytic functions as terms, I do not need the exponential functions. But on the pieces, so for the pieces, I need the exponential functions. The following easy example. So let big fxy be, of course, the semi-algebraic function y minus x. This if y is bigger than x and 0 else. 0 else. Now small fxy is the log-analytic function f of x log y. Then fxy equals this term here if y is bigger than exponential function of x and 0 else. And you see here I get something like an exponential term. Okay, I could avoid it, but if I want to describe it with respect to y, I get this term here. And now from this point of analysis, dividing light, it seems to be obvious that the logarithm does not introduce non-quasi-analyticity or flatness. Piecewise, this is clear since the terms behave nicely piecewise. But the challenge is to control the behavior on the boundary. So where these pieces come together. And to control the behavior of log-analytic functions on the boundary, the idea is, again, use the work by Lyon-Rolla, use the preparation theorem of Lyon and Rolla for log-analytic functions. Note these preparation theorems have been extended later on by Van den Vries and Speisecker to a more general situation. And here I want to give you these preparation results. So x runs over r to the n, y over r. Let's see in Rn times r be a definable set. And by Pc, we denote the projection of C onto Rn. So P is a projection from Rn plus 1 to Rn, so projection on the first n coordinates. And preparation results means monomial times unit. Whatever are the monomials, whatever are the units. But this is the idea of a preparation result. And here I want to present the notion of the monomials. So a tuple y0, yr of functions on C is called an R logarithmic scale. So this is the same R with center theta, the tuple of functions theta 0 up to theta r, if the following holds. The functions theta j are definable functions on the projection pi c. And these tuples yj, they are obtained by translation by theta, applying the logarithm. So in the case j equals 0, we have yj is y minus theta 0. In the case j bigger than 0, we have yj is logarithm of the absolute value of yj minus 1 minus theta 0. So applying logarithm, translating. Of course, I have omitted here some technical details. So this yj minus 1 is not allowed to be 0, and so on. So that's a logarithmic scale. So once again, applying logarithm, translation. And if I have a function on C, we say that f is r log analytically prepared with respect to the variable y. If I can write fxy as a product where the factors here, the first factor is a function depending only on x. Here, monomial, so here the logarithmic scale with some powers, and here unit. So what is a unit? Being away from 0 and from infinity. So, where this here is an R logarithmic scale on C, these exponents are rational numbers. A is a definable function on the projection of C, and U is a unit on C. This means it takes values away from 0 and infinity. And we have additional properties on U. How does U look like? There also this logarithmic scale comes into the play, but it's rather technical. It's a rather technical, so I omit the presentation here. But this is the idea of preparation. Factor depending not on y, here monomials, logarithmic scale times a unit. And here the preparation theorem by Leon-Rollin. If I have a log-analytic function of order R, then I find a definable cell decomposition C of the ambient space such that F restricted to every cell C is R log-analytically prepared. But what is the problem? The problem is that the preparation theorem can in general not be performed in the log-analytic category. Why? Let's go back. You see, here these theta j's are definable, but in general not log-analytic. Here we might have exponential terms. Or here, the function a is in general definable. So a might have exponential terms. Also u. So this is the problem here, that the preparation theorem can in general not be carried out in the log-analytic category. Example. Consider the function phi defined on the positive real line. T is mapped to t over 1 plus t. And now I consider the following real analytic function. xy is mapped to minus 1 over log phi of y minus x. Then f is log analytic of order 1. We have 1 times the logarithm, but there is no log analytic preparation of order 1 or stronger of any order with log analytic data only. So if I fully prepare it on this space, then I get some pieces where in the data, in the preparation, I have exponential terms. Why? Well, I take the compositional inverse of phi, which is psi, which is, well, at 0, more or less the geometric zeros, the geometric series minus the constant. Then, what is the zero set of, what is a zero set of f? Well, fx c at the point E minus 1 over x is 0 for every positive x. And if I prepare f around the graph of this function, I see that I get really terms in the preparation where I have the exponential function. Okay. So from the point of analysis, the idea is that we need some situations where we can use the preparation theorem, but where the preparation works with log analytic data only. So the idea is prepare log analytic functions on special cells. In this, what is our special cells? So I have a definable cell C, where the last variables are only positive. And such a cell is called simple if it's between y goes between 0 and a necessarily definable function alpha from the projection to the positive real numbers. So y moves from the coordinate axis to some graph. And why it's enough to consider such simple cells? Well, often the variable y is introduced as an advisory, as an additional variable. But in the X space, it's enough to consider simple cell. That's the following remark. So let's see the definable cell composition of Rn times R greater 0. Then Rn is of course the union of all projections of cells in C, but it's even the union of all projections where I just take the simple cells, just by cell decomposition. Because for every X, I have to prepare every Y. So then I find a Y which is close to 0. So for the X space, it's enough to consider the simple cells. And this is now our simple preparation theorem. To prove this, we have to go again through the proof of Lior-Rolla, respectively Van and Speisecker, to adapt the proof, and then we get the following. So let F be on this space, be a log-analytic function of order R. Then there is a definable cell decomposition C of that space, such that the restriction of F to every simple C in C is R log-analytically prepared with log-analytic data only. And with this result in hand, we are able to establish the following theorems. Here we come to the theorems. The first one is closeness undertaking derivatives. So let U be an open set in R to the n, and let F from U to R be log-analytic. So U is of course here definable. Now let I be an index such that F is differentiable with respect to the variable xi on U. So that the partial derivative of F with respect to xi exists. Then this function is again log-analytic. Once again, term-wise, piecewise, this is trivial because I can use this description of log-analytic functions piecewise by terms, but to get this on the boundary, I need this preparation result. And I need this simple preparation. And why? Where is here the y? Well, y is the new variable that this y goes to 0. That's the very definition of the derivative of the difference quotient. Okay. Next result. We have really strong quasi-analyticity. Theorem B. So let U be a definable domain in R to the n, and f from U to R be a log-analytic function. Then there is a natural number big N with the following property. If f is Cn, and if there is an A in U such that all derivatives of f up to order n vanish in A, so let's say that this means that f is n flat at A, then f vanishes identically. So n flatness implies 0. And that's strong quasi-analyticity. So quasi-analyticity means flatness implies being 0. Here, even n flatness implies being 0. And finally, we can adapt the arguments of Van den Dries and Miller to generalize Thom's theorem from globally subanalytic functions to log-analytic functions. So let f be a log-analytic function depending on x and y. Then there is an n in big N such that the following holds for every x, y in Rn times Rm. If so, x is now fixed. If fx is Cn at the point y, then this function is already real analytic at y. So once again, of course, this big N depends on the function f, but once the function f is fixed, we have not all Cn's. We can have C1, C2, C3, and so on, up to C big N. But from C big N, we have C omega, we have real analyticity. Okay. To conclude, so I was a little bit fast, but I avoided to give the technical details. So to conclude, from the point of view definability, from the point of view of definability, the logarithm gives everything. But from the analytic point of view, the logarithmic point, including the logarithm, so joining it to the globally subanalytic functions, I do not get new analysis. That denied theorems can be generalized from the globally subanalytic setting to the log-analytic setting. And this is our result. To have a little bit more insight what's happening with respect to analysis in this very important omnivore structure ANXP. Okay, thank you very much for your patience.